Yeah, but the notation is very confusing.
Yeah.
Why don't you just use X star there? Oh, I mean,
Yeah. Here, suppose we consider a classification problem. Here is a class 1, and here is a class 2.
yeah, actually, I get it, but you still have typo there. The first equation should be X star there also. And the second equation has the X star there, X star.
So suppose we consider a classification problem. Here's a class 1, the distribution of class 1, here's the distribution of class 2. Then in SVM, we will consider those points as the support vector. Other points are not support vector. So here the omega I associated with those support vector are not zero, otherwise they go zero. So this is a linear definition of the kernel function. Okay. And so in this case, we cannot use maximum likelihood because if we use this, the omega is not sparse, so we need to take into account the information of the square. So we suppose the square is omega either 0 or 1 or can be any level. So when we want clarity, the omega, the vector omega is not sparse. We can find the square. If the square distribution of omega is very sparse. So if we suppose it's uniform, so in this case, we can introduce the sparse acquired distribution for omega, which can make omega is sparse. The best choice is using a conjugate distribution of Gaussian because we suppose everything is Gaussian. In this case, we can get multiple functions. We suppose the omega has a Gaussian distribution. So we introduce a new parameter alpha I for each of these, and alpha I is the inverse of the variance in a normal distribution. And in this case, there's a zero mean, and there's a variance 1 over alpha I, and then we have omega 0. So we have alpha 0 to alpha. So if we set the most of alpha is very large number, then the probability of omega is 0 is very large. Here the Gaussian distribution for maybe alpha 1. Here's another distribution for alpha 2. In this case, alpha 2. larger than alpha 5. So the larger the alpha, the shape of the distribution has a sharper and so if we can count the alpha, most alpha has very huge infinite value, then we can guarantee omega is sparse.
It's the other way one. I know what you said, but when you say it, it's like when alpha is large, what do you just say?
When the alpha is large,
Then
the shape of the distribution is
Sharper? Like more narrow, you mean?
Yeah. Here, alpha is the inverse of the variance. And so we can introduce another prior for alpha. Make sure alpha is very large. So this is a gamma distribution. Here A and B is another two parameters to make sure alpha is very huge. The value of alpha is very huge. You can set the A equal to or even you can set it to 0. In this case, alpha is very huge for the gamma distribution. Actually, in the real calculation, we set A and B equal to 0. So we don't need to care the value of A and B. And in this case, alpha, the most alpha is very huge. The value of alpha is very huge. So this is the property of gamma distribution. And you can repeat since we introduced the prior distribution for with I, then we can write out the probability for omega. Here's a vector into the O and given alpha to the product of Gaussian function. So here is the prior distribution of OB. And if we take this prior information into this function, we can rewrite the probabilistic prediction formula as this. Here we introduce a new parameter, alpha. This term is very easy to calculate. It's just equal to according to the Markov property. Here, T is the get rid of alpha from this additional probability. Then for this one, we have we already have the definition of this probability is equal to a product of a lossy function. So we append to the first item. So for the second item, we can write the second term. Here we introduce term, and then for the first term, we got the